Welcome to the lecture on Newton's third law of motion. Newton's third law states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Or to put it in a more traditional way, to every action there is always an opposed equal reaction. This means that every time you exert a force on something, it is going to exert a force right back on you. So if you punch a tree, then the tree is going to hit you right back and it's going to hurt, even though the tree is not in itself doing anything. This immediately seems to be a contradiction of Newton's third law, which said that if there are no net forces, then there's no acceleration. If every action has an equal and opposite reaction, or every force has an equal and opposite force, then how does anything move? The way we deal with this is to carefully define a system. So as long as the system doesn't include all of the forces, the reaction and the action force, then you're fine. So for example, on the left-hand side, we have an apple pulling an orange. And because we're only worrying about the orange, we don't have to worry about the reaction force of the orange pulling on the apple. However, this isn't very satisfying. So a more complete answer is that generally there are going to be forces which are acting in the opposite direction, which we just don't care about or don't pay attention to. For example, if we include both the apple and the orange in our system, the two forces, the force of the string pulling on the apple and the force of the string pulling on the orange, will cancel out. But the force of the apple pushing back on the earth will cause the earth to push back on the apple and move it forward. This is how we walk. We push backwards on the earth, and the earth pushes us forwards. Looking a bit more macroscopically or looking a bit more microscopically, depending on how you look at it, there are nearly uncountable number of interactions inside a football in the form of chemical and gravitational forces between atoms, but each cancels out another, leaving no net force to accelerate the football. In order to accelerate, there must be a force from outside the system, for example, a kick, which creates a net force and accelerates the football. The kicker's foot would also accelerate in the opposite direction with an equal force acting on it, but would not accelerate with the same acceleration. To illustrate this, we look at a cannon which shoots a cannonball. Both the cannon and the cannonball will experience forces going in opposite directions with equal magnitude. However, the force divided by the small mass of the cannonball leads to a large acceleration, whereas the force divided by the large mass of the cannon leads to a small acceleration. This is also true of rockets, which accelerate by shooting out a bunch of what the book calls molecular cannonballs towards the Earth to push themselves forward and into the sky. An example of these action reaction forces, which we have been talking about without defining, is something called normal force. Normal force is the reaction force when one object is pushing into another object. If this occurs, then the other object will have a reaction force, which is designated by N in these drawings, which is called the normal force. It is always going to point straight out the surface that your object is lying on. It can be used to explain why the acceleration of a block of ice on a ramp will get higher the steeper the ramp is. So for example, if the block of ice is just on a horizontal surface, the normal force will be pointing straight out of the surface directly opposite to the weight mg, which is going to cause there to be no net force whatsoever. However, if you uh, put the block on the ramp as seen in the second and third figures, you will start to see that the normal force goes down as the angle of the ramp goes up. Using our trapezoid rule, we'll see that the normal force and the weight creates a resultant force vector that points down along the ramp. If it pointed into the ramp at all, then there would be more normal force, which would cancel it out. So normal force has to be exactly enough that it cancels out the part of weight that's pointing into the ramp. So for the second and third examples, as the ramp gets steeper, the portion of weight that's pointing into the surface gets smaller, and the normal force also gets smaller. This is also going to cause there to be less friction because normal force is proportional to the weight, but not necessarily equal to it. In this case, as I said before, we can engineer situations where the normal force doesn't have anything to do with the weight. So the acceleration gets bigger until it reaches this point where you're on a perfectly vertical ramp and the normal force is going to be zero because the weight is completely parallel to the surface of the object. And normal force is named normal force because normal means perpendicular to a surface. So the normal force is always perpendicular to the surface. And if there is no force to balance out perpendicular to the surface, then there is no normal force. As another example, we have a monkey on a vine clinging to a cage. Because the monkey is pulling the cage towards it, the cage is in turn pulling the monkey towards it, which is going to be pointing to the right. The tension T is the force pulling from the rope and is pointing along the direction of the rope. The force from the cage is written as S. In order for this to hold true and for the monkey to not fall, tension and S have to form a resultant vector which cancels out mg. So looking at T and S, you see that if you find their parallelogram is pointing and find the resultant vector is pointing straight up against gravity, causing no net force. Similarly to the cannonball, the gravitational force between the Earth and the Sun is the same, but their acceleration is different because acceleration is proportional to 1 over m. So gravitational keeps planets in orbit around the sun, but the planets of our solar system are small enough that the acceleration of the sun is essentially zero. This might seem weird because the Earth is moving at a constant speed, but if you think back to chapter 3, at the end of the lecture, there was an example of an object moving at a constant speed in a circle that was still experiencing acceleration because the direction of velocity was changing. This means that basically gravitational acceleration is going to only affect planets orbiting the sun rather than the sun itself. However, if there are bigger planets or smaller stars, you see a wobbling effect on the star as the acceleration becomes more noticeable. And this is actually how we are able to detect exoplanets, which are planets that are outside our solar system. We look at stars and see whether or not they wobble. And if they do, then that means that they have a really massive planet that's circling around them and causing an acceleration that's noticeable to us from the Earth.